Hello, everybody, and welcome again to your channel, Thermal Engineering Concept and the Principle. This is the second part, which is related to the cylindrical objects, where we have studied the heat conduction in these geometries, where there is a heat generation per unit volume. And in this part, I will introduce another boundary condition, which is the practical one in the application of these geometries when they are accompanied by a heat generation per unit volume. Thank you for your support, and thank you for following this channel, which is 3. So the objectives can be attained by sending these information to anyone who needs them. Let us start with the objectives of the present episode. The main objectives of the present video are related to the heat generation in cylindrical coordinates, where we will study the convection part in those geometries, and we will reduce the three-dimensional form of the steady-state condition to one-dimensional heat conduction, some applications in real engineering, and then some case studies, which are the practical cases where can be found in the industrial field. Finally, the closure for the present video, and we will pass through the content which has been already covered in the present episode. The heat conduction equation in cylindrical coordinates, if we have a look at this schematic diagram in 3 dimensions, x, y, z, which represents just a piece of a cylindrical object in the coordinate r, z, phi, and that will give us just a sort of schematic diagram where we can apply the heat transfer by conduction in this piece of, for example, solid cylindrical object, and the heat transfer usually is perpendicular to the heating surface. The three-dimensional form of heat transfer by conduction in a cylindrical coordinate is represented by equation number 1, partial square t with respect to r square, plus 1 divided by r partial t with respect to r, plus 1 over r square, and go on until we approach the right-hand side, which represents the rate of change of energy inside that wall. If we consider that the definition for alpha, which represents the thermal diffusivity as K, the thermal conductivity of the material divided by the density of the material times the heat capacity. And usually it is in the units of meter squared divided by second. So for one-dimensional form in steady state, and that means we will take it in the direction of r, radial form, d squared t by dr squared plus 1 over r dt by dr plus q dot divided by k equal to 0. And the right-hand side is equated to 0 because there is no change in for the temperature of the cylinder with time. This equation can be represented in a form that multiply all these terms by r. Then we have the mathematical expression that d by dr of r dt by dr plus rq dot divided by k equal to 0, and that will give a produce for the first integration as rd t by dr equal to minus q dot r squared divided by 2k plus c1, which is represented by equation 4. And if we proceed for the second integration, then we will get t of r equal to minus q dot r squared divided by 4k plus c1, a natural logarithm of r, plus c2, which is represented by equation number 5. And this equation, I will call it the magic equation for the cylindrical surface. Some of the practical applications in industry and in our life in engineering, that is where heaters are used in washing machine, where it is used to heat up water for a certain temperature as the setup of the process in that washing machine. And then we have in the boilers where we produce hot water, such as the boilers are used in domestic places. Also, we have in the kitchen where we can find this in the sort of heater is used for the purpose of cooking of our food. And then we have another application which is called industrial application, and these forms may be used in industry in a variety of applications, such as air heaters, where we use for heating purposes. Let's pass through the convection boundary condition. And we have here a solid cylindrical object with the outer diameter of d and length of l, which is a component with a heat generation per unit volume q dot, and it is exposed to the ambient fluid, which has the convection parameters HA and TA, and we need to find an expression to describe the temperature distribution in the radial direction under the steady state conditions. So the solution, as usual, starts from the magic equation d squared t by dr squared plus 1 over r times dt by dr plus q dot divided by k equal to 0. And when we made two successive integrations, we have obtained equation number 5, which represents the temperature variation in r direction in terms of q dot, thermal conductivity, and the radius. So the first integration or the derivative, the first derivative for the general form, dt by dr equal to minus q dot r divided by 2k plus c1 divided by r, which is represented by equation 4 as it has been obtained before. And we have two boundary conditions. The first one, r equal to 0, dt by dr should equal to 0. And if we apply this boundary condition to equation 4, then we will end with C1 equal to 0. And in boundary condition 2, where the R value equal to capital R, that means at the surface of the element, then T equal to T sub W, or wall temperature, that will give us C2 equal to T sub W plus Q dot capital R squared divided by 4K. If we go back and substitute these values in equation number 5, then we will end with equation number 6, which represents the temperature distribution in the radial direction equal to T sub W plus Q dot divided by 4K times capital R square minus R square, which at the end, it depends on the value of the position inside that cylindrical object in the R direction. So if we think about the heat generation per unit volume in terms of the convection part, at the cylindrical object surface where small r equal to capital R, we have q dot r squared times pi times L, which represents the value of q, equal to h sub a times 2 pi times r times L. 2 pi RL represents the surface area of the element times the temperature difference T sub W minus TA. Therefore, T sub W equal to T sub A plus Q dot times capital R divided by 2 times H sub A. This is the wall temperature of the heating element in terms of the ambient conditions. And if we substitute the value of TW in equation number 6, then T of R is represented by equation number 8, which gives the temperature distribution in the radial direction in terms of Q dot capital R H sub A and the thermal conductivity of the cylindrical object. Then T of R equal to T sub A plus Q dot capital R divided by 2 times H sub A plus Q dot divided by 4K times capital R squared minus R squared, which at the end, it is a function of R. Here we have an example with the numerical values for heating element, in fact, which has a diameter of 10 millimeters outside diameter with a length of 3 meters, and it has a rated power equal to 3000 watts, and the temperature of the heating element is kept at 90 degrees Celsius. It is exposed to oil, thermal oil, which has a temperature of 40 degrees Celsius. The question is how to find the heat transfer coefficient of the oil, which is outside the heating element, when a steady state has been considered. And at the same time, we need to estimate the heat flux at the heating surface. The solution of this problem, we should start from the calculation of the amount of heat generation per unit volume, which equal to Q dot equal to power divided by pi divided by 4d squared times L, which represents the volume of the heating element. Then we will end with a value equal 12.732 times 10 to power 6 watt per cubic meter. This is the amount of heat generation inside this element. The heat generation at the heating surface should equal to the amount of heat dissipated to the thermal oil under steady state conditions, because there is no energy accommodation inside that element. If we substitute the values and we talk about the general volume, Q dot times pi r squared times L, then we will get Q equal to H sub A times the surface area, 2 pi capital R L, times the temperature difference. And T sub W then we will be obtained from the equation 7, which has been already found before. And that will give in term of H sub A, because T sub W is known, Q dot also known value, capital R, TA, all these values are known. So we may substitute all these values, and we should pay attention for unifying the units. Everything should be consistent. Then we will get H sub A equal 636.6 watt divided by meter square Kelvin. This is the first requirement, or the first attempt to solve this problem. Then we have found the heat transfer coefficient. And the second part, which is related to the heat flux at the heating surface, is equal to Q divided by A. We have Q 3000 watt divided by the surface area of the heating element. Then we will end with heat of flux amount to 31.831 kilowatt per meter square. This is the answer for the second part of this example. Now let us pass through one of the practical application in industry, of course, that where we have electric current of 100 ampere is passed through nichrome wire of K equal to 13 watt per meter degree Celsius, and the diameter corresponds to 3 millimeter. If we assume the electrical resistivity of the nichrome as 1.12 micro ohm times meter, and the length of the wire to be 1.5 meter, the wire is submerged in a liquid where heat is dissipated to that liquid, and it was at 80 degrees Celsius with heat transfer or convective heat transfer coefficient of 1200 watt per meter square degree Celsius. Then we need to calculate the temperature at the center and surface of the wire, And we need to sketch the radial temperature variation through the wire, and that means we have only one-dimensional heat conduction, and this should be considered under steady state conditions. The solution for this problem is similar to the general form uh, of heat conduction and cylindrical object where it has heat generation per unit volume. The resistance of um, the thermal resistance of the wire is equal to rho times L divided by A, cross-sectional area of the wire. If we substitute the value of rho, here represents the electrical resistivity of the nichrome, and then we will get the resistance to be 0.2377 ohm. Of course, we know that the power equal to I square the current times R electric. That will end with 2377 watt. This is the power generated by the heater or the nichrome wire, and power equal to H times A surface times T sub W minus T infinity, and that will give T sub W equal to T infinity plus power divided by H times the surface area of the heating element. Of course, if we substitute the values of T infinity equal to 80, power equal to 2377, and H, the heat transfer coefficient, 1200 watt per meter square degree Celsius, and we have the surface area of the heating element that will end with T sub W equal to 220.1 degrees Celsius, which represents the first answer for this example, and Q equal to Q dot power divided by volume, which represents the heat generation per unit volume. And if we substitute the values of the power and using the dimensions, diameter and length of the cylindrical wire, then we will get 224.2 megawatt per cubic meter. R equal to D sub wire divided by 2, which represents the outer radius of the wire, equal 1.5 times 10 to minus 3 meter. And we have T sub R represents the temperature distribution in the radial direction, equation number 6. If we substitute the values and use R equal to 0 at the center, then we will end with an equation T naught equal to T sub W plus Q dot divided by 4K times capital R square. And substituting the values will end with 229.8 degrees Celsius. This is the answer for the temperature at the center of the heating element. And we have T of R as represented by equation number 6, T sub W plus Q dot divided by 4K times R capital R square minus R square. Then that will end, if we use different values of R, 0, 0.25, 0.5, 0.75, 1.0, 1.25, and 1.5. This is the value of R. Then we will get the temperatures as it has been calculated for the center to be 229.8, and as we go away from the center, the temperature falls down 220.1 at the surface of the heating element. And we may plot this table, the results of this table. We have X and Y. X represents the radius and Y represents the predicted temperature. Then we will get a curve just like that, the red one, and it shows the temperature falls as you move from the center, which has the maximum value, down to the wall temperature, which is around 220, which is exposed to the fluid, and it has a convection part of heat transfer. And this part, which represents the closure, we passed through the heat conduction, where there is a heat generation in the cylindrical object under steady state conditions. We have introduced the convection boundary conditions, which is the practical application for these heating elements. Usually they are used in air conditioning for as air heaters, and they may be used in industrial applications or even in the domestic applications, just like ovens and microwaves. So usually we have a convection boundary condition, and we passed through some exercises, workout exercises, and then we have to mention that there is a list for some references to be found in a link in the description box. And thank you for listening and passing through this channel content, and I hope that you may subscribe and share the information with others. And I will see you in the next episode in other applications of heat transfer.